Let's understand the general form of oscillator circuit. We have seen so many phase shift oscillators. Now we will see general form of oscillator circuit. This is an amplifier. This is operational amplifier here. It can be a FET or a BJT or an operational amplifier. The important parameters that need to be here are in very high, that is input resistance to the amplifier should be very high, output resistance should be low, and we should have voltage gain as negative. We need minus AV. So these are the characteristics that we require in the amplifier. It can be operational amplifier, it can be BJT based amplifier, or it can be FET based amplifier. So this is about this thing. Then we have this impedances. This is a network of impedances, Z1, Z3 and Z2. Why impedances? Because they can be resistance or capacitance or inductance. We will see what they are. So let's say this is Z1, Z3 and Z2. Then the net impedance will be this. See, Z1 plus Z3, this I is 0. So Z1 plus Z3, these are in series, parallel Z2. Okay, clear? What it will be? It will be Z1 plus Z3 into Z2 by Z1 plus Z2. See, keep on writing whatever I am telling you. We'll later on replace these impedances with capacitances and inductances. Those circuits are called Colpitts oscillator and Hartley oscillator. So whatever we are deriving now, you will just have to put the value L or C there, and you will get a Hartley or a Colpitts oscillator. So Z is this. This is the diagram explaining this circuit. That is, you can see this is voltage series feedback. The feedback network is in voltage series feedback form, this feedback network. And whatever the gain we have, whatever type of amplification device we have, this will be like this. AV is the voltage gain and V13, that is this to this voltage. Here see 13, this is ground actually. So whatever voltage you have, if this is V13, so this is amplification of this, and RO is the resistance in the output of this amplifier. Okay, so this is the, which I told you, Rin is very large, RO is low. So this is a schematic representation of this circuit only. So clear up to now? Then we'll proceed further. Now if you have any confusion, you can go back and see the picture. I have rubbed the board because I have to write equations. The gain without feedback is what? AV into, we have ZL and RO. See, this was RO and this was basically ZL. So this is actually this into ZL by ZL plus RO. Okay, so this expression you should keep in mind. And the feedback factor that we had, this was Z1 and this was Z3, and we were taking from here. So this is actually equal to Z1 by Z1 plus Z3. This portion was actually being sent to the input point. So beta is Z1 by Z1 plus 3, and our gain without feedback is this thing. AV is the voltage gain of the amplifier, ZL by ZL plus RO. So if you put this, we have to get this equal to 1. So if you multiply it, minus A into beta, see, A is this and beta is this, and AV you know what it is, or ZL you know what is ZL? ZL is basically Z1 plus Z3 parallel Z2. This is your ZL. So putting these three, this is 1, this is 2, this is 3. You get minus AV Z1 Z2 by RO into Z1 plus Z2 plus Z3 plus Z2 into Z1 plus Z3. Okay, so this is the expression that you get. You have A, you have beta, you have ZL. So if you put these values minus A beta will be equal to this thing, AB, Z1, Z2, RO into this thing. Okay, I am rubbing this. Now, if this Z1, Z2, Z3, this network Z1, Z2, Z3, if they are pure reactances, that is, they are either capacitors or inductors, they are not resistors. If that is the case, then you know Z1 can be written as Jx1, Z2 can be written as Jx2, and Z3 can be written as Jx3. So now you can put these values. See, Z1 into Z2. So J square, so this minus will be gone. So you can write AB is equal to AB into X1, X2. J square minus minus cancels. Similarly, you have this. See, so you will have J, you can take J out, R0. This will be X1 plus X2 plus X3. And here you can take one J from here and one J from here. So that will be minus J square, and this will be X2 into X1 plus X3. Okay. So this is the second most important expression. This and then this. From here we have a very interesting relation. We want to have this equal to 1, this equal to 1, and this is only possible when this is a real number. This factor cannot be present, because if you have a J factor, this will be a complex number and your A minus A beta cannot be 1. Therefore, from here we get X1 plus X2 plus X3 should be equal to 0. This is the first condition. Okay. So if you put this condition, what you get? So this is 0 here. So what will get? A beta is minus. So minus AV, X1, X2, X2, X2 cancels. So X1 by X1 plus X3. So this is the second expression that we get. That is, for this equal to 1, from Barkhausen criterion we know this has to be equal to 1. So for this equal to 1, and also you need to have 0 phase shift or phase shift equal to 2n pi. That is possible only when you have pure, this should be a real number, not a complex number. So from there we get that this quantity should be equal to 0, and when we have put this quantity equal to 0, we get minus A beta equal to AV X1 by X1 plus X3. Okay. Or you know, X1 plus X3 is minus X2. So you can write it like this also. This will be by minus X2. So AV X1 by X2 also. So you have minus A beta equal to this, or you can write like this. Okay. Now from this equation, you see this plus this plus this. What needs to be understood, that our frequency of oscillation omega or F will be from this only, from this equation, that is, are those 1, 2, 3, Z1, Z2, Z3 in series. So the combination of this, the frequency of this circuit, the omega that we get from this circuit will be the frequency at which this complete circuit will, this oscillator will resonate. So if this is RLC or if this is LLC, whatever be the frequency of this combination, that will be the frequency of oscillation of this complete oscillator. Okay. We have a very interesting result from this. See what I have written there in the last page. A beta is AV, then X1 by X1 plus X3, or X1 plus X3 is minus X2. So this is AV X1 by X2. Okay. This is the expression. Now AV is always greater than 0. We, by negative voltage gain, we meant minus AV. But this AV, the magnitude is always greater than 0. For this to be positive, if this quantity has to be positive, because we need this minus A beta equal to 1. So for minus A beta equal to 1, this has to be positive. This means that x1 and x2, this should be of same type, that is either they are capacitors or they are resistors, inductors. So x1 and x2 are of same types, either they are capacitive. Why? Because we have, if you remember, j omega L and 1 by j omega C, that is minus j by omega C. So these two have to be of the same type, then only this is possible. And x3 is what? It is minus x1 plus x2. Now, if these two are of same type, we have to get a minus out of it. Therefore, if this is C, this will be L, and if this is L, this will be C. That is, x1 and x2 are of same type, either C or L, and x3 is the other one. Okay. So this is the general form of oscillator circuit. Based on this concept, we have two circuits. First is called Colpitts circuits and second is called Hartley circuit. I am drawing the figure and then we'll understand. The expressions we already have done. Let's understand it. So based on the discussion that we had just now, we have two circuits. This circuit is called Colpitts oscillator. Colpitts oscillator. And this oscillator, this type of oscillator is called Hartley oscillator. Okay. You see, this is BJT based amplifier where we have minus AV as the gain. This is collector resistance, this is RE, this is R1, R2, all for biasing. This you know. Okay. In Colpitts oscillator, you have two capacitors here. See, C1 and C2 and this. So this is Z1, Z3. So here what you can write is your Z1 is minus J by omega C1. Your Z3 is minus J by omega C2 and your Z2 is J omega L. So in expressions you can put this value and you will get everything, A, beta, AV and all. AV is from this only. So you will get all the values, you will get the value of omega also. So this type of circuit where you have two capacitors here and one inductor here, that is Z1, Z3 are capacitors and Z2 is inductor. This type of circuit is called Colpitts circuit. The exact analysis of these circuits is very difficult because there are so many issues. The input resistance is not, infinite. So this can shunt the input resistance. So these things are to be considered in actual circuits. Whatever expressions that we have arrived at, you can put these values and get your expression for basic theoretical reasons. Similarly, we have Hartley oscillator where we have L1, L2 here. As Z1 and Z3, you have L1 and L2 and you have a capacitor here. R1, R2, RE, RC, you know what is. So this will change. Z1 and Z3 are now J omega L1 and J omega L2. And this is minus J by omega C. So you can put these values in and you will get expressions for Hartley. Okay. So what we actually do, we remember the general form of the oscillator circuit, and as per the question whether it is Hartley or Colpitts, we put these values. So this is about Colpitts and Hartley circuit.